Hello everyone! In this video we will continue examining topic 5.2, the heating effect of electric currents, and in particular Kirchoff's circuit laws, and a return to Kirchoff's second law. Okay, so now we're going to apply Kirchoff's second law to a bunch of different circuits, all right? And our analysis is going to be a little bit overly detailed, but I want to make sure that everybody sort of moves forward with these examples and understands what is happening physically, because that's super helpful in applying this equation. Okay, so we're going to apply this equation to the circuit that we analyzed in the last video. This is example A. Okay, so this is the one we looked at here. And I'm going to skip ahead, sort of this was our final result. But I want to point out what that looks like on a potential position graph. Okay, remember this position doesn't mean, it's not scale, it's not centimeters or whatever, it just keeps track of sort of general regions. And what we're going to look at with potential versus position here is as we go around the loop, okay, so what does this mean? What does our loop mean? Well, we can literally map these that pink loop onto this graph, okay? So if we start here, for example, right, at arbitrary 0 volt potential, then we go up epsilon 1 or 2, doesn't really matter the order, but up the first EMF, up the second, down the first potential drop, down the second. Notice that I have drawn these so that delta V1 and delta V2 are different, and that EMF1 and EMF2 are different, but it doesn't really matter. They could be the same, so you would need the particular values to know what was going on, okay? So now let's take up another example. Before I move on, note that the takeaway from this is that if you have two cells in series, which is known as a battery, okay, so this is where we're actually correctly using the word battery. So two cells in series like this, as long as they're in the same direction, they add up for the potential difference. Okay, so if this is 3 volts and this is 5 volts, then the total potential gained will be 8 volts top to bottom. Now let's take a look at example B, all right? Example B has something interesting going on. The first thing to recognize is that we're going to have EMF and EMF1 and EMF2 and R1 and R2 in different places, okay? So how would this affect the circuit? Well, we apply Kirchoff's second law, we draw our loop, and then we keep track of the different elements. Our first element is EMF1, okay? And then we are in the same direction as the current, so we are going down the potential for R1, so minus I1 R1, and then we go up the potential gain for EMF2, that's positive, then we go down the potential drop for R2, that's minus I2 R2, but of course I1 is equal to I2 because everything is in series, and so we solve it out and we get exactly the same equation that we had in the first case, okay? So in series, the order doesn't matter. Now, I will say that a map or a graph of the potential as you go around the circuit will be different, okay? So if we start here at 1, that could be, for example, at 0 volts. Then we go up EMF 1, then we go down delta V1, and we go up EMF 2 for some size of EMF 1 and EMF 2, and then we go down delta V2. And so the order doesn't matter, and that's one of the things that comes out of Kirchoff's second law. All right, now let's take a look at a trickier example, although still semi-intuitive. So now what we're doing is we're going to analyze this circuit. Notice that compared to this circuit, there is one change, which is that this cell, or this battery, has changed directions. Okay, so it's reversed directions in the circuit. That's the only change, okay? So now we draw our loop, all right? And at this point, it's not obvious what direction the current is going to go in, right? You can think of it as like, is EMF 1 going to win and drive the current this way, or is EMF 2 going to win and drive the current this way? Well, as you might imagine, it depends on the relative size of EMF1 and EMF2. But for our analysis, it doesn't matter. Why? We simply pick a loop direction and then keep track of our minus signs. So we pick our pink loop direction as before, except now, instead of positive EMF1, we have negative EMF1, because now we're dropping through the potential difference across that first battery. So we go negative EMF1 plus EMF2, okay? Notice it doesn't matter what order I do this in, negative EMF1 plus EMF2, because our current as drawn is going in this direction, okay? Then we keep track of delta V1 and delta V2. So we've drawn the current this way and we've drawn the current this way, which means that this is minus IR1 minus IR2 equals 0. Okay, so the only thing sort of driving the current in this hypothetical example is EMF2. So I'm sort of assuming right now that EMF2 is sort of stronger than EMF1. It's larger. If that's not the case, what will happen is if I solve this completely out and put my actual values in, my current will simply be negative. It will end up negative from the algebra. All right? And conceptually, you can think of it either in either of these forms. So this is the EMF2, and it needs to account for the reversed EMF of that second battery, sort of subtracting plus driving the current through these two resistors. Or conceptually, some people find it easier to do this. The actual EMF driving any current at all is going to be equal to the difference between EMF2 and EMF1. All right? And this is an abnormal case. So this is sort of, quote unquote, a miswired thing going on. So what is happening in our abnormal case here as the current goes through EMF2? Well, the current is going down or in the reverse direction in the battery, and that is with the loop direction. And we are going from higher potential difference to lower potential difference as we cross EMF2. As a result, delta V is then negative EMF1. So this is an abnormal case. We're driving current in the wrong direction through the battery. Notice that some batteries will not do this. So in practice, don't set up circuits like this. Some will be fine, but some are not designed to run current in the sort of quote unquote wrong direction, and they can explode in one form or another, which is no good. So given that, all right, what does our potential graph look like? Right. So now we say, okay, we're going to start here again. So here we're at 0 potential, and then we're going to drop through EMF1. Okay, we're dropping through EMF1, and then we drop through delta V1, and then we rise through EMF2, and then drop through delta V2. Notice that because EMF1 is miswired, right? It's backwards. Delta V1 and delta V2 end up very, very, very small. Another way of saying it is that because you have this battery sort of fighting EMF2, is a way to think about it, the actual current that ends up driven through R1 and R2 is very small. And that the effective EMF applied to R1 and R2 is just the difference between these two things. So if this is EMF1 and this is EMF2, then it's not surprising that delta V1 and delta V2 end up very small.